Let's talk about interdynamic mesh motion solver. Okay, so here we going to look at the few aspect of VOF and as well as the mesh motion together. Okay, so that is the idea behind this if we talk about interform, so interform is the multi-phase solver. Okay, and it facilitates the basically the VOF class of application. So let's first have a look about that particular solver. Okay, so application solver, multi-phase and interform. Okay, so this is all the code about the interform. Okay, so let's first explore the interform. So go to the C file. So solver for two incompressible isothermal immersible fluid using a VOF, volume of fluid method. Okay, phase fractional base interface capturing approach. Okay, so we able to capture the interface, sharp interface between liquid and the any of the gas. Okay, so that is the idea behind that. So and it by default enable the laminar runs and alias modeling. Okay, so that is the idea behind that. And when we talk about this interface tracking, at that time we going to use the MULES methods for volume fraction point of view. Okay, so that is what we required. Okay, so let's first observe the few equations that we're going to solve here. Okay, so VOF base, so what we have a liquid phase, liquid volume fractions. Okay, so in that we say alpha is, let's say, alpha 1 or alpha 2, or let's say defined with the simple alpha is the volume fraction for liquid and 1 minus alpha is the alpha 2 is volume fraction for gas. So in that way, if we look at the effective density is nothing but rho into alpha rho L plus 1 minus alpha rho G. Okay, or you can say alpha 1 and alpha 2. Okay, or alpha liquid and alpha gas. Okay, so but alpha characterize the volume fractions. Okay, so if alpha equal to any place 1, then we say that that cell belong to the liquid part. If alpha equal to 0, that cell belong to the gas part, and in between then it is half way, or based on the alpha quantification, it is filled with the liquid and air both. So in that class of the cell we find out the interface between the liquid and the gas phase. Okay, then we're going to solve the transport equations. Okay, so transport equation for volume fractions, that is alpha. So here we want to solve the transport equation for volume fractions. So this is nothing but del alpha by del T. This is convection of that particular interface, and this is short of something like a diffusion we're going to add on it. Okay, so that is how one can see these equations. Then mass and momentum equations, continuity equations, and we have a momentum equation. Here we have body force, surface tensions, and some other pressure forces. Okay, so this is nothing but surface tension force, and we have to specify the surface tension value through the transport property area. Okay, so this is what we're going to solve all these sets of equations. Okay, so let's have a idea about this all the equations and how we're going to look at the things. So let's go towards first interform. So look, interform and the dynamic interform. Okay, so interform with the dynamic mesh motion, what is the difference? Here it's still the solver for two incompressible isothermal immersible fluid using a VOF, phase fractional base interface capturing approach, but idea is that we have a option for mesh motion and mesh topology change. Okay, that is the possibility. So everything is same as far as the interform and the dynamic form is concerned. Only thing is that in dynamic form we have a mesh motion class of the things is activated. Okay, so first have a look about the interform. Okay, then we go towards that area. So interform, we if we see, then we have a FV options. Okay, turbulent transport modeling is available, so we can activate the runs and alias modeling. Okay, so first let's look at the create field file. Okay, so create field file suggests about the our one equation. So if you look at here, so rho. Okay, so rho is nothing but alpha 1 into rho of liquid, alpha 2 of rho into rho of gas. Okay, so same way you can see here. So rho 1 and rho 2, it is about the first phase and second phase. Same way alpha 1 and alpha 2 for first phase and second phase, and from that we are constructing the rho as alpha 1 into rho 1 plus alpha 2 into rho 2. Okay, so that is quite visible from this area. Now if we look at here, the second equation is about the mu. So this we coded towards the let's say transport model area. So let me guide you to that area. So that is not available in the application part, it is available in the SRC folder. Inside the SRC folders we have a transport models. Okay, and inside the transport models we have an incompressible area, and inside the incompressible area we have incompressible two-phase mixture. Okay, and inside this two-phase mixture, if we look at this .c file, we are able to identify that area. So calculate nu and calculate mu. Okay, so this is the member function. So here we able to quantify the mu out of it. So we say, okay, alpha into rho into nu. So rho into nu give us the mu. Okay, so nu, because in the OpenFOAM we work with the nu. Okay, so that's why you find here nu, and the rho of that particular phase. Okay, so rho 1 and plus we have alpha 2, here we have alpha 1 minus alpha 1 is equal to nothing but the alpha 2 into rho 2 into nu. So this is exactly the same equations what we are looking at. Okay, so these equations we will see from the this area. Okay, two phase transport model area. Then we have another equation is this alpha equations. Okay, so that is nothing but the liquid volume fractions equations. So that we're going to solve as a alpha equations. So this is the alpha equations, and okay, let me first start with the interform so we have idea about that. Okay, so what we are looking at, we are starting the calculations. Okay, then alpha equation subcycle dot h. So let's go there, alpha equation subcycle dot h, and here we have a different way to treat the alpha. So based on the number of cycles we specified from the solver part, it try to calculate the alpha equations that many time. Okay, so that is the idea. And here how we are constructing based on the alpha the rho quantity that is needed for Navier-Stokes equations, and from here we are calling the alpha equation dot h file. So that is here alpha equation dot h file, and in this basically we are solving this one equations. Okay, so that is how it is coded inside of this. Okay, so and then we have a Navier-Stokes equations. So continuity in momentum, it is same way what we see in the normal scenario. We have a first pimple, within the pimple loop we have a momentum predictor, and then we have multiple correctors. So let's look at the U equations. So if we look at the U equations, in case of our normal all the terms, okay, we have additional terms like surface tension force, and this is nothing but the gravitational force. Okay, and this is nothing but our pressure term. Okay, so this all the terms whatever we see here 1, 2 and 3, it is available. Okay, inside the Navier-Stokes equation, all other terms are almost same. Okay, so now if you look at here, we have additional entry like surface tension force. Okay, so surface, if you want to look at the code for this surface tension force, then just copy this area. Okay, go to our oxygen area. Okay, so if you go to a oxygen and search this quantity, you will able to find out that entry. Okay, here and here interface property surface tension force, that is what we are looking at for this particular models, and here is interface property dot c file. Okay, so if you go inside of this, you will find out exactly where this particular properties is calculated. Okay, so it's supposed to be like a calculate k. Okay, so that is this interface property. Okay, and here we try to take into account the surface tensions. So, and we're going to read the surface tension from transport property dict file like sigma. What we going to specify the sigma inside the transport property, from where we're going to read these particular quantities. Okay, so that is how one can see that how exactly it is take into account inside the OpenFOAM. Okay, so this couple of the things, if we are interested towards the coding part, then we have to go inside of this all the entries. Okay, otherwise there is no need of it. Okay, so this is the Navier-Stokes equation and how it is take into account. So let's go back to this file. So we solve for first alpha. Okay, then from the alpha we find out the rho value. With the help of the rho, we go towards the momentum equation, then the pressure equations. Okay, and then we, if we are turbulence, then we have to correct the turbulence, and then we come back to the again the pimple loop. Okay, so this is all the how it is coded inside the interform. Now let's look at the interdynamic form. Okay, so this is the interdynamic form where we have a mesh motion unable. Okay, so that is the difference we have here about the mesh motion solver. Okay, so what we see in here, we supposed to modify the mesh, so that's why we have mesh update options available. Okay, and few more change we required. Okay, so reference gravitational references and all these things. Okay, otherwise basic equations is more or like same. We going to solve for same u equation in the p equations and the alpha equations. Okay, but here we have a mesh motion, so certain peripheral change is required. If mesh is changing, then we have to calculate again the fluxes. Okay, so relative and the absolute fluxes, whatever we required. So that is what is coded in this area. Okay, so this give us the basic as idea about this interform and interdynamic mesh motion form. Okay, so let's now try to look at few tutorials and have an idea how exactly one can simulate the couple of very simple test case based on not interform but interdynamic mesh motion form. Okay, so that is the idea behind this particular discussion. So here I am starting with very simple like 2D sloshing tank class of tutorials. Okay, so for that let's go to this area. Okay, and let me also guide you to certain few more aspect. Wait. Okay, so let's first explore this very simple tutorial that is about the sloshing tank tutorial. Okay, so for that let's first create the environment. Okay, and let's clean the case first. Block mesh, paraform, have an idea about the our geometry. Okay, so this is the some class of the tank. Okay, and we fill the liquid and the air in it. Okay, and then we try to give the some specified movement to this particular tank. Okay, and try to look at the how the inside liquid is moving within this tank. Okay, so that is the idea. It is called sloshing of the tank. Okay, and for that we require certain settings, so we try to explore few settings whatever we required. Okay, so but this is the basic our geometry. So first let's set up the test case. Okay, then we try to understand. So I just clean the our alpha.water file. Okay, now please understand this this liquid is always over the first fluid. Okay, so always whatever you specified in that our phase property, first based on that you have to specify this alpha. Okay, so I will come back to again that point. Okay, but first let me say set field. So with the help of the set field, what we are doing, first understand that. So inside the set field we say that by default everywhere alpha of water equal to 0, but within this box we say alpha of water equal to 1. So when you do that, what going to happen is something like this way. Okay, so let's look at the alpha of water as a concentration point of view. Okay, so alpha of water, if we see, so this is the how we look like. So in this area we fill the water, and remaining area is open, sorry, it not open, but where we have air. Okay, and how we make sure it is air and that thing. So for that you have to go to the constant area, okay, and just look at the transport property file. So look, phases, whatever the phase you define first, for that we have to specify the alpha. Okay, if you say air first, then we have to specify the alpha for air. Okay, if you say water first, then we have to specify alpha for water. Okay, and this is its simple property, mu and rho. Okay, so that is the and here is the surface tension. Okay, if you want to give the surface tension, then you specify here. If you don't want, then just say 0. But we require this sigma as entry. Okay, why it's required now? Now you understand, because that entry at the end goes in the momentum equations. Okay, so that's why this entry is required. So from here in the transport property we have to specify the phases. Okay, so we say first phase is alpha 1, second phase is alpha 2. Okay, so always whatever is the first phase, it is important for us. Okay, and depending on the first phase only we try to set up the entire equations. Okay, so if we say air is the first phase, then inside the 0 folder we supposed to say alpha of air. Okay, not the alpha of water. Whatever you specify here first, it goes in the 0th phase as alpha. Okay, so we say alpha of water or alpha of this thing. Okay, so that is what we needed from this part. Okay, then let's look at both the entries. Okay, so what we say for all the walls, it is a moving wall. Okay, and for pressure we say it is a fixed flux pressure. Now inside the constant folder we have to specify the solid body motions. Okay, so for that we are using the solid body motions FV mesh solver, and we are working with the SDA, solid body function as a SDA. Okay, so for that, if you want, we can check how exactly different entries is available inside of it. For that, very nice Wikki is available. Okay, so let's explore that area. Wait a minute. Yeah, from this area. Okay, yeah, okay, so here it is give us the specific. Okay, 1 minute, let's go back there. So SDA is a motion specific to modeling in a marine application. So normally for the marine applications, people are using this particular entries. Okay, SDA create this prescribed motion in a 3 direction: roll, have and show. Okay, this was introduced to simplify the motion of vessel in a subway. Okay, so sorry, seaway. So this is allow us to fix the certain motions. Okay, and for that purpose we have to rely on this SDA couple of entries. Okay, so in the SDA we have a set entries available like SOFG, that is nothing but center of gravity, lambda, that is model scale ratio. So normally in real life our actual model is very large, and right now we are working with, let's say, scaled model, so we have to specify that ratio. Roll MX, maximum rolling amplitude, minimum rolling amplitude, have amplitude, show amplitude, damping coefficient, time period for liquid. Okay, natural period of ship, current roll period, reference time steps. Okay, increase in TP per unit DTI. Okay, so if you are interested, please go through each and every entry. Okay, so whoever are working in this area, they can appreciate all these entries. Okay, so they have a proper definition of each and every terms. So I suggest, if you are interested in detail, please go through this area. Okay, and have a look of all the entries. Okay, how they are calculating rolling movement and rolling parameters. Okay, all these parameters they mention here. What is mean by TP? Okay, TP parameter, how it going to affect? Okay, so based on your requirement you can tune this parameter, but here very detailed aspect of each and every entry is mentioned. Okay, so based on your requirement, I suggest please go through that entry. Okay, along with that, I find very nice this one report. Okay, so I'm also keeping that report here, so you also please go through it. Okay, somehow it not opening for me. Yeah, maybe this is the problem. Yeah, so here they discuss couple of the things. Okay, like all these few entries about all the motions. Okay, so translations, motions. Okay, so this is show, surge, then this is yaw, pitch. Okay, rolling, have, all this definition they mention very nicely in this one report, and all other quantification also they mention. Okay, so and some different class of settings you can see from this area. Okay, so have an idea if you are interested in this particular entries. Okay, it is mentioned in this area, so please have a look about it. Okay, so this is all how we can set all the different values. Okay, so this is along which we have a rotation or any of the movement, so CG, center of gravity of any of the solid body. Okay, so that is very important, and all other entries that is mentioned here. Okay, and so with the help of that we specify the movement. Okay, so solid body, what we do, we at a time we specify the movement based on this all the entries, and based on this specified movement it now try to rotate. Okay, or move according to this all the movement. Okay, so that is the idea. It is solid body motion, so entire solid is moving with respect to this particular set motion. So that is the idea behind that. Okay, and then along with that we definitely have a G term and the turbulence property. So here we are working with the laminar flow. Okay, and then in the system folder we have all this file. So control dict file, we have a solver, we are running till 40 seconds, let's say. Okay, and as a probe we have a different on the probe we can quantify the pressure, or if you are interested different thing you can look at that. Okay, so probe and wall pressure, so on the all the walls how the pressure is applying. So normally how it goes, if we have this pressure information, it that information one can feed for the structural solver and find out the what is the material property required to sustain this class of the sloshing in the tank. Okay, so that is sometime goes toward the FSI class of the problem. Okay, so sometime people what they do, they try to club this inter form and dynamic mesh motion, and along with that fluid structure interaction part as well. Okay, and have a idea exactly what going to happen when we talk about the sloshing of the tank. Okay, and exactly how the different forces is applied on the walls. Okay, so that is sometime if you are interested then you can quantify that all the quantities from this. Okay, schemes, so we are working with the Gaussian Van Lee schemes. Okay, and otherwise we are working with the center difference schemes. Okay, and the solver part, now we are solving for alpha equation as well, so we require this alpha dot water. Then this is the cycles. Okay, sub cycles, so if you see that alpha is not converging then you have to increase this value. Okay, then this is correctors and pressure part. Okay, pre-final. Okay, then we have a smooth solver for U equations. Then if you want the momentum predictor on, then you go with that, otherwise let it be off. Okay, and that is the outer corrector 2. Okay, then we have a non-orthogonal correctors. Okay, then reference pressure value and the relaxation parameter. Okay, so these few entries help us to look at the convergence for our simulations. Okay, now let's calculate this very simple test case and have an idea how exactly it is working. So look, from here first pimple loop is started. Okay, and we first specify the mesh motions based on this SDA entry. Okay, so it try to give the motion, and then we solve for alpha. Okay, and then we solve for pressures. We say momentum predictor no, so we are not predicting the velocity, but we directly based on the pressure we are correcting the velocity. Okay, so that is the idea behind that. Okay, and this is the current number. Yeah, very important aspect here is this current number. Okay, it's supposed to be low. Okay, and we normally work with the adjustable time step in case of the this when we talk about the interform viewer based applications. Okay, at that time it is always better to work with the this current number. So we have alpha based current number and the this normal current number. Based on that, they try to find out the optimum delta t that will support both the current number. Okay, so that is the idea. Okay. Now have a look at how exactly the tank is moving. So here is the how the tank is look like. Okay, and what we have a alpha as a quantity. Okay, so alpha we say as a volume fractions here. Okay, so let me first look at like this way, and here is x. Okay, so look, this is the mesh motion is specified for this tank. Okay, and it is a solid body motions. Okay, and depending on these motions, so entire liquid, that is water in this case, is moving within this tank. Okay, so you can consider this is the cross section of the tank, and we are looking at how exactly the entire water is moving within this tank. Okay, so that is the idea. And when it is moving, what is the pressure loading and everything one can see on the its wall. Okay, so let's go towards post-processing area. Okay, so if you look at here, this is wall pressure. Okay, and we have a raw data as a wall pressure. So this raw data is straight away goes, okay, and help us to, let's say, let me open this particular entry. Okay, yeah, post processing, this one, let's say this. Okay, so this is the raw data XYZ and the pressure. Okay, so on the entire of the wall, at each and every location, what is the pressure distributions. Okay, and this goes as a feed for the structural solver sometime, and people try to look at the or analyze the strength and the deformation of the structure based on this pressure loading. Okay, so this is also very useful when we talk about this sloshing of the tank and all these things. Okay, then we also stored the probe in this area. Okay, so if you are interested, go and just post process the probe as well. Okay, so we have a probe location for pressure, so we set a probe at a two places basically. Okay, so and over the probe we try to look at the how the pressure is varying within the entire of the tank. Okay, so but this is very simple example of the specified motion, but important aspect here is this dynamic mesh dict file. Okay, so we have to set all this entry based on our mesh motion requirement. Okay, so for that we have to understand each and every entry in this SDA part. Okay, so if you are interested, then please go through it and try to understand each and every entry, and based on your requirement you can tune this entry and have a entire idea about this mesh motion solver. Okay, so I also in the previous case also I run, and I just showed here the mesh motion for entire of the case. Okay, so depending on the movement of the tank, the water is oscillating here and there, and when it is oscillating, it try to impose certain forces on the structural or the wall of this particular let's say tank, and that is what needed for the designing part of the particular this tank. Okay, so that is what one can see from this tutorial. Okay, now let's look at the this is where we specified entire motion to entire of the solid body. Okay, but sometime it is not required. We are interested to let's specify on some portion of the entire of the our computational domain. Then it is something like this way. We are saying, let's say this is one of the let's say object and is moving within the environment. Okay, so either it's move in this direction or it can move in any other direction and create the let's say movement within the enclosure. Okay, so if we want to set up this class of the test case, then what we require, let's explore a couple of the things with respect to that. So let's look at the readme file, okay, and go to that area. Okay, so let me open. Okay, and first let's clean the case. Okay, so we have a then block mesh, paraform. Okay, so this is our geometry. Okay, and what we have at this box is this wall. Okay, so we try to specify the movement to this particular box. Okay, and along with that, what we do that we already look at when we talk about the dynamic mesh motion. So at that time we able to specify this motion to this particular box in the linear, oscillating, rotating, all this thing we explore. But now we club the VOF in it. So that is the idea behind that. Okay, so let's first clean our alpha file. Okay, and then we say let's say set field. Okay, and when we run the set field, what we're going to achieve is something like this way. Now we have alpha for water in a specified area, so we fill the half of the enclosure with the water and half is filled with the air, and now we specify the movement of this particular object. Okay, so now what we require from the dynamic mesh motion dict file, we need not to specify the motion here. We specify the velocity Laplacian or velocity component Laplacians, all this thing, and along with that we have to work with this diffusivity part that you remember from our previous tutorials. Okay, so here our box is let's say oscillating, so we say box here. Same way in the previous our case we say move. So same entry I kept here. Okay, so let me modify this. Okay, so everywhere it is box. So depending on the our mesh, we have to tune these parameters so that the mesh not going to distort. Okay, so that is what you supposed to do from this side. And now we are working with velocity Laplacians. Okay, so when we work with the velocity Laplacians, additional file, that is the mesh motion for you, is required inside the zeroth folder. So let's observe this, and from here what we do, we going to specify the mesh motions. So as I show you two videos, so this is mesh motion based on that both the videos. Okay, so let's say we specify sorry, let me fix this area. Okay, that is fine. Okay, so here I can specify the linear displacement. Okay, you can create your own test case for based on the previous tutorial and merge this concept and have an idea what is going on. Okay, so I say the oscillating displacement, and the amplitude I specify as a 3. Okay, in the x directions. Okay, and this is the its frequency with which it is coming and going in the particular x directions. Okay, so along with that we have a entry for all these things. So let's have an idea. So in this is the original file, but then we try to apply the set field over it. Okay, and here we say box and the tank. Okay, we say moving velocity. Okay, wherever we required, and then we say fixed flux pressure over it. Okay, so that is what we have. Okay, now let's try to run this case. Okay, and have an idea how exactly it is creating the motion. Okay, so let's quickly check how the motion is look like. Okay, so paraform. Okay, let's open the volume fraction as well. Okay, and now let's look at the motion. So look, when it start moving, so it is filled with the water halfway. Okay, so it is moving in one and another direction. So because of the motions, the water is moving and creating the oscillation within the enclosure. Okay, so I already run that case for longer time. Okay, so let me open the file. Okay, so this is what you can see if you run for a longer time. Okay, so that is one class of the motions. Okay, and then let me clean the case again. Okay, and generate the other motion as well. Okay, so let's filled. Okay, and then we have to modify the motion U file. Now I don't want to give in the only one direction. I want to give the movement of the block in the diagonal directions. Okay, so I specify like that way, and then again run the case. Okay, so if you look at, we have a variable delta t based on the current number. Okay, we solve for cell motion U. So when we have this cell motion, so please remember that we required a certain few more entries inside the solver area. Okay, so in this all the entries required. Along with that, we also required the cell motion U and cell motion U final, these entries. Okay, that is what we needed, and we have to specify that entries. Okay, now let's look at the paraform and the mesh motion. And then let's check how exactly the motion is look like. Okay, so this is till now what we constructed. Okay, and I already run that case. Okay, so I will show you its animation. So I suggest please run it and have an idea about how exactly the motion is look like. So depending on the motions, the now water is start moving inside this enclosure. Okay, so based on this movement, the entire enclosure is getting the water fluctuations. So that is the idea behind that. Okay, so this is another class of very good example where we can specify the motion to any particular wall. Okay, now let's very nice example we have. It is, let's say we can specify certain movement to any of the block, and it is filled, it is falling on some of the water surface. Okay, so it is called the falling object type of the tutorial. Okay, so let's have a idea about that tutorial as well. Okay, so I am showing you couple of examples. Okay, so whatever is you think it is applicable to your project area, you can adapt couple of the things from these sides. Okay, so let's first clean the case. Okay, falling object. So for that, what we require, let's first remove the 0th folder. Okay, and first construct the block mesh files. Okay, so and then we have a topo set. Okay, so what we're going to do, from the block mesh we try to construct one cell zone 0. Okay, within this box area from entire domain, and we say invert it. That means we try to remove that box, this whatever the element is fall within this cell zone C0, we try to delete that zone, because what we required, we were to construct the geometry for the object. Okay, so whatever the object we want to construct, we try to construct based on this. So let me show you what exactly going to happen. Okay, so this is entire of our domain. Okay, so within this domain what we're going to do, we try to construct the small portion within this domain, and we say invert it. That means we say C1 invert. What it going to do, it try to delete the whatever the cell within that C1, and it try to give us only the surface of that particular box, 3D box. Okay, that is what going to happen. So let's run the topo set and have an idea. Okay, so here is the topo set command. Okay, now again if you go towards paraform, okay, and just look at the wireframe, okay, and then say all the sets. Okay, so sorry, it we till didn't finish. Then we say subset over the C1. Okay, and then we have to we will get what we required. Okay, so with the help of the topo set, we try to construct that particular cells. Okay, and then we say subset of it. Okay, so what we did, we try to delete the cells within that. So how we are sure what exactly happened? So for that, let me cut the plane that passed through that particular area. Okay, so that is fine, needed. Okay, so look, we cut that much portion. So and what we achieve out of it, we define the wall for that particular object. Okay, so that is what we have here. So this is the floating object wall, and for that we going to specify the particular motions, and with that motion it try to fall on some of the liquid surface. So that is the idea. So let me quickly set our set field. Okay, so with the set field, what we going to do, we going to specify the alpha as a water volume fractions. And now just check our test case how it look like. So let me quickly set this. Okay, and what we required the alpha. So here is how we have this alpha sets with this, and if you want to look at the inside, you can say opaque it. Okay, so you can see within this. So here is the object. Okay, and now what going to happen, this object we give the motions in the free motions. Okay, it try to fall on the water, and when it fall on the water, it try to part up the water, and that is what we're going to see out of it. Okay, so that is the idea behind that. Okay, fine. So let's start the simulation for that. Okay, so before we start the simulation, let's look at the settings whatever we required. So in the constant folder, we just look at the few entries from this area. Okay, so first is transfer property. Okay, so we say phases, water and air, and for the water we specify the property, for air we specify property, and we also specify the surface tension. Then turbulence, we say K epsilon base model we're going to use. Okay, G in the Z direction minus 9.81. Okay, and here we again specify the 6 degree freedom class of the solver. Okay, 6 DOF rigid body motion solver. It is a very powerful motion solver. It 6 degree of freedom is what? 3 translation motion X, Y and Z, and 3 rotational motion with respect to X, Y and Z directions. Okay, so depending on our requirement, we can fix or leverage the motions whatever we require. Okay, so that is the idea behind this. Okay, so this is how we can set the 6 degree type of the solver or motion solver. Okay, 6 degree freedom motion solver one can set from this area. Okay, and we have to specify the degree of motion on for this particular patches. So that is the wall of the our falling object. Okay, then inner distance and the outer distance, it is very important. So whatever is within the inner distance, it's behave as a like a solid object, and with that it try to move ultimately based on this particular object along with that. Okay, and whatever is in the within in between inner and the outer, that class of the mesh is going to change. Okay, or move, mesh going to move based on the whatever the solid body is falling and everything. Okay, then we require the center of mass, moment of inertia, rho infinity. Okay, report on, that means it try to give you the all the forces that is required on the object. Okay, acceleration relaxation parameters. Okay, then we have a this is dummy value, and the solver wise we have a 3 options available at this particular solver level. Okay, and then we have a certain constraint, so we can fix the movement, even though here we have a 6 degree of motions. Okay, but if we want to constrain the motion in one particular directions, let's say we don't require the motion in XY direction, but we require motion only in the Y direction or Z direction, so we can fix the motions. In same way we can fix the axis that is about the angular motions. Okay, so with this you can fix that it going to rotate in only one particular axis. Okay, so all these things you can constrain whatever we required from this area. Okay, so that is whatever we needed, it is possible from this particular area. Okay, so that is few things we can set or leverage the mesh motions whatever is needed. Okay, so this is 6 degree of freedom class of the solver we're going to use, where we can specify the 3 translation and 3 rotational motion based on the X, Y and Z direction, or we can fix the motions in particular directions wherever we require. Okay, so that is the idea behind that. Now just go to the 0 folder and have an idea about U file. Okay, so whatever is the floating object wall that is moving, okay, in other all is the atmospheric condition we are specifying. Okay, for pressure we say it is a total pressure type of the condition at atmosphere, and on the floating object we say it is a fixed flux pressure. Okay, so that is what we going to specify on it. Okay, and floating object we say this point displacement we say it is calculated. Okay, if needed it try to calculate based on the requirement. Okay, so this is how one can set the 6 DOF class of the mesh motion on a very simple class of the geometry. Okay, now let's run this particular test case. So before that let's check the mesh. Okay, and then let's say renumber the number of element if you want. Okay, it helps to reduce the bandwidth of our matrix. Then let's run the case. Okay, so I don't have any animation file for this particular test case. Okay, otherwise I will show you very quickly what's going to happen. Okay, but no problem, it's going to finish at least couple of iteration very quickly. Okay, so this is let's look at the alpha. Okay, and then let me opaque so that we will able to see what is happening inside. Okay, now we will give the release this particular object. Okay, so it try to go inside. Okay, when it hit the surface it try to give the oscillation to the our water object, and because depending on its weight and the center of gravity it try to move and oscillate, and finally it goes toward the steady state nature. Okay, so that is the idea behind this entire. Okay, yeah, so look, it almost entered inside the our water object, water body. Okay, and depending on that it try to create the wiggles on the our entire of the water body. Okay, so look, it try to release. Okay, and then it try to bombard on the on this particular surface. Okay, so let me Okay, so I suggest please run this case and have an idea, okay, about the this interface movement, okay, how the interface is moving when this particular object is hitting the water surface. So for that, let's cut the plane so it gives us little bit more idea. Okay, so it is exactly passing through this way, so let me cut it in the y directions. Okay, fine. So, and let's see that. Okay, so this is how it's look like when it's hit up. Okay, so from here it started, enter, okay, and slowly try to trigger the motion. Okay, then it's going to come out of it. Okay, so this is called 6DOF base motion solver. So here we have only one object. Let's say we have multiple object, then what to do with this class of the movement? So for that also we have a couple of nice options is available. Okay, so I suggest please run this case. Okay, now here we look at the one object. Let's say we have a two object. Okay, so here we have multiple options: two object with a coupled motion, two object with an uncoupled option, two object with a one object you can specify the motion. So all these options is available. So how to set up this different class of the test case, have an idea about it. Okay, so let's say case number one. Here we say the two object, but it is coupled way moving. Okay, so when it is coupled way moving, what it mean, slowly I will let you know. Okay, but first let's observe or have an idea about this entire test case. Okay, then we talk about this all the things. Okay, so let's first create the environment for this particular test case. Okay, so clean the case. Okay, then let's construct the mesh. Okay, then topo sets. So look, in the previous case we have only one object we constructed, so we work with the only one topo set. Now we have a multiple object we want to construct. Okay, so what we're going to do, we first use one topo set. Okay, and we construct the C0 as a cell, and we invert the cell so that we remove that portion from that particular mesh. Okay, so that is the idea. Then we say subset C0 patch floating object. So we constructing all the boundary from this. So we add expose internal faces to the patch floating object. Okay, so in the first command we remove the cell. So now we remove, so internally we find out the expose internal faces. Now we say all the faces goes to the floating object 1. So now if you see paraform, you will see one object is already created. Okay, so this is how it look like. This is one object we constructed. Okay, let's say now let's construct the another object as well. For that we have another topo set. So what you see from inside the topo set 1 and 2 is nothing but the box coordinate. Okay, so where we want to extract that particular box, so we require the two corner of the box, and then we say let's construct the C0. Then we say invert it, that means we remove the cells whatever is available within that particular box. This is for topo set 1 and topo set 2. So with the help of that we construct the cell zone 1 and 2 and we invert it, so we remove that cell zones. Okay, that is the idea. Now let's look at the topo set for second part. Okay, so we constructed it, and then we say whatever the exposed face we have, we try to look at in terms of the floating object 2. Okay, so that is the idea. So we constructed floating object 2 as well. So now if you go here, okay, and check the entry, so we have a 2 object, that is what we constructed, and here is the object 1 and 2. Okay, so 1 and 2, and then we have a atmospheric sphere at the top, and all other are the stationary walls. Okay, so this is all the walls, and top is the atmospheric conditions. Okay, and these two object, and what we're going to do, we try to use the solid body motions, okay, and try to look at the coupled wave motion for this. So for that we rely on dynamic mesh motions, okay. So we say 6-degree freedom of motions, okay. And here, depending on the size of the object, okay, what we do in the previous case, we keep the CG within one of the object. Now we have to specify the center of mass, okay, depending on both the objects center locations, okay. Then the cube dimensions, okay, rho, that is the density of solid. From that we calculating the mass, okay. And for moment of inertia we are using the this code entry, and we try to calculate the moment of inertia for that. And then we have a constraint, and so line constraint we are specifying, okay. And the axis constraint we are specifying. That means it's we only leveraging the y motion as far as the rotation is concerned. We are not allowing the object to rotate in x and z directions, okay. That is what we are specifying here, okay. And then here we also, as far as the line is concerned, okay, so center of, sorry, this is about the axis, okay, and this is center of line. So here when we say center of rotations, we have to specify the center part, okay. And then we say we only leveraging only the y direction about the rotations. Both are as a fixed direction, so we constrain that way, okay. And solver, we have a new mask, then Crank-Nicolson and Simlic. 3 options is available, okay. So if you misspell it, you can find out what different options available at that solver level, okay. So now let's try to look at few more entries. So here we don't have a option to specify the different motions for each of the object, okay. So that's why we say patches. As a combine, we specify patches for both the page, okay. So it is a coupled wave motion one can see, okay. So that is what we needed from this side. Then what else we required? We required in the 0th folder, we required the boundary conditions. So both the object is moving in the similar line. We have other boundary conditions, so have an idea about this, all the boundary conditions. And then let's first clear the copy the 0 folder, or sorry, 0 org folder to 0 folder, and construct the 0 folder. Now apply the set field, so we construct the alpha for water, okay. And then before we start, just look at how exactly it's look like, okay. So let's see alpha, okay. So this is how we look at the, and if you look at the OPEC, we can see internal part, okay. So this is how, here is our 2 object, okay. And we gave the motion to be leveraged with respect to the y-axis only, okay, not with respect to x and z axis, okay. So that is what we're going to observe when we start the calculations, okay. So we are set for running the test case. First let me renumber the matrix, and then we are running. We specify certain codes, okay. So it try to include the things and link the code and compile and try to give us the moment of inertia, okay. That is what is going to happen internally, okay. So now it is running, okay. So have an idea what exactly happened. We fix the coordinate number, first pimple loop. It try to use the 6 DOF rigid body motion solver, okay. And look at first center of mass, center of rotations, orientations, okay. Then linear velocity, we only leverage in the y directions, and we leverage in the angular velocity as a z directions, okay. So if we don't leverage this, then it try to go in any direction, but we specify a particular constraint, and we say it's only able to rotate about the y-axis, and translation also with respect to y only. We don't want any other class of translations. That is what you are seeing from this, okay. And for alpha, we are using MULES, okay. That is also you can see okay, and volume fractions for phase 1 is that much what we are seeing here. Okay, so that is how one can see the progress. Let me quickly check the simulation how it look like. Okay. So let me keep it something like this way. Sorry, let's look at the alpha from, and also let's construct the opaque things. Okay, so now this is how it look like. Okay, so we, depending on, this is object. Okay, so depending on the weight of the object, it is try to freely move on the water. Okay, so that is the idea behind that. Okay, so now look, we only give the rotation based on the y-axis. Okay, so if you look at in this direction, you will not see the rotation with respect to that particular directions. Okay, here, and even velocity also we gave in the only the leverage in the y direction only. Okay, so that is how one can see from this side. Okay, so that is what we specify the motions. Okay, so that is we restricted its motion in the particular directions. Okay, basically. So this is how, as a coupled wave, we can specify the motion. But let's say we want to specify uncoupled way of these motions. Okay, then what to do? Here we don't have options. If we look at from the let's say dynamic mesh files, we cannot have a to separate this object for individual object. No, it's not going to work that way. Okay, so how to set up this uncoupled motion? So for that we have a certain way to take into account that entries. So let look at that, how one can set the uncoupled motion as well. Okay, so for that let's go to the next test case number 2. Okay, where we have an uncoupled way of looking the both the object. Okay, so let first look at the files. So everything is same, nothing difference, we only specifying the motions different way. So let me quickly set up everything. Okay, whatever we needed up to here. So we constructed the both the object, then we copy the 0 folder, and then we say set field. Okay, so everything is set. But now let's check the motion entry. So for look at the dynamic mesh file. So in the dynamic mesh file, what is needed, we require the libfe mesh solvers additional entry along with the 6 DOF entry. Okay, and when we work with the libfe motion solver, we have to specify what type of the solver we want to work. So let's work with the displacement Laplacian, velocity Laplacian, velocity component Laplacian. Whatever you needed, you can specify. And then we require the, when we work with the displacement or anything, we require the diffusivity. So for both the cases we are specifying the diffusivity, but all the setting now goes inside the 0 folder. Okay, so org, and we specifying the point displacement. Okay, so within the point displacement, if you go to this file, okay, so what we have a this, but now we have for floating object 1, we specify here the 6 DOF motions, and whatever the motion you have to set for individual object, you can specify 6 DOF motions. Okay, constraint, restraint, whatever you required. Okay, so depending on your requirement, you can set the motion for each and individual patch from here. Okay, and that is very, very handy. I say you can individually specify the motions whatever the way you required, but when you are specifying individually, make sure your center of rotation supposed to be changed. Okay, so few change you required, like same way we have to shift the center of mass. Okay, and the center of rotations. Okay, moment of inertia we're going to calculate inside, so we need not to worry. Okay, so 6 degree body motion constraint. Okay, so in the rotation wise we are giving the rotations. You can check, you give the rotation to another object and check how it is happening, all this thing. But idea is that here we have to specify separately for each and individual object different entry, and depending on this it will uncoupled way, I say, you can set the motions or take into account the 6 dF for each and individual object. Okay, so let's quickly run this case. Okay, so we set for this, yeah, up to that. Now let's run this case. Okay, so here we are specifying, look, 6 dF for each and individual body. Okay, so this is for one body and this is for another body. In the previous case we have only one 6 dF motion combined. Okay, but now we have a totally different motion for individual body. Okay, so this is the I say very nice way one can set a motion very quickly. Okay, so this is possible with the help of this particular options. Okay, and have an idea how exactly the motion is look like. Okay, so we require the alpha entry. Okay, and then let's opaque the surface, so at least we see internally what is happening. So now it is moving individually. Okay, so now you see the motion is completely different as compared to the first one. Okay, because in the previous case we have a combined effect at a time. All the forces as a combined we are taking into account the rigid body motions, but here individual object, depending on the its characterization within the flow, it will try to move accordingly. Okay, so that is the difference we have. Okay, now let's say we want to specify the predefined motions to one of the object. Okay, and another object is like floating, so that is also possible. That is our third example. Okay, so we try to give you some different idea. Okay, how to you can set up the test cases. So in the third one, again the concept is more or like same. We have to construct the 3 blocks. Okay, sorry, 2 blocks, and but what we try to do here, we try to specify the certain type of the motion for one class of the block. Okay, so that is the idea. So this is case 1, let's say block mesh. Okay, and for topo set 1 2 3 and set field up to here we are set. Okay, so we are set with this, but now what we require in the 0 folder, go here. Here first object we say 6 dF rigid body motion, but for second we are specifying oscillatory displacement motions. Okay, so depending on the oscillation of the second block, the first block try to perturb. Okay, so that is the idea behind that. And similar line you will see the entry in the dynamic mesh, same what we see in the previous test case, same lib FV motion solver we have to specify, and 6 dF rigid body motion one has to specify, and then this all the diffusivity and all different things. Okay, now everything is same, just run this case very quickly. Okay, so here we have only one 6 degree of freedom motions, but another object is moving with respect to the particular motion that is specified for that particular object. Okay, so that is what one can see when we look at the post processing of this particular test case. So let me get inside of our domain. Okay, now what we try to do, we try to specify the motion to one of the object. Okay, and depending on this motion, this object also try to perturb. Okay, so that is the idea. Slowly, so that is what one can specify. So there is a different ways one can set emotions. Okay, and depending on that motion, so another object may move here and there. Okay, so let me cut the plane in the z direction. Almost it's supposed to pass through. Okay, so this is our cut plane view, y directions. Okay, now just check. So we are specifying these motions. Okay, so when we specifying the motion, slowly this object is also try to oscillate. That is the idea. Okay, so when you run for a longer time, you will see or observe, because of these oscillations, how the second object is also affected. Look, when it try to construct the wave, that wave is triggered and try to hit this object, and it also start oscillating. Okay, so that all the things one can see. Slowly second object is start to oscillate. Okay, so that is the how one can check the prescribed motions, and because of the prescribed motions, what different changes is appear. Okay, so slowly it try to oscillate. Okay, so please try to run this case as well. Okay, so this is the how you can specify different class of the motions. Okay, on the simple object. Now we have one last tutorial about this dynamic form, that is about exactly the boat, and it is something like this way. Okay, so we have a prescribed, sorry, 1 minute. So this is the boat. Okay, and it is on the ocean. Okay, and depending on the movement of the this so this is moving from left to right. Okay, it try to give the perturbation to the boat and the hull. Okay, so that is the idea. Okay, so and it try to rotate. So we try to look at the 6 DOF class of SDA class of the things here, not 6 DOF. Okay, so we look at the so yeah, sorry, we talking about the 6 DOF only. Okay, I have an idea that it is SDA, it is 6 DOF. Okay, and we say hull and hydrofoil. Okay, so that is the small portion is the hydrofoil. Okay, and we say center of mass, moment of inertia, and all these things. Okay, and then we have a constraint, and then we have a restraint. So restraint allow us to look at this some linear damper or spring angular damper class of the restraint. Okay, so if you want to specify the damping movement, or based on the your understanding of the structural dynamics, you can restrain the movement of the object. Okay, so that is possible in with respect to the constraint we are restricting the movement, but with respect to restraint we are damping, or sometime we are facilitating the movement, and based on the spring mass balance and all that concept. Okay, so if you are interested, if you have a knowledge, you can incorporate that all the concept in here as well. So we have a restraint and the constraint, both the options is available. Okay, so this is all entries we have to set as a 6 DOF. Okay, and let's quickly try to set up that test case. Okay, so so here we are working with the snappy hex mesh. Okay, so that is the mesh generator, that is what we're going to use. So first let me clean the case. Okay, so this particular test case going to take a very long time. Okay, so we just set up the test case and then we stop there. Okay, so let's first generate the mesh with the help of the snappy hex. Okay, so STL file is provided, and based on the STL file and the all the refinement setting, layered settings, so based on that it gives us the very nice mesh. So meanwhile, let's look at the few entries in the this. So we say hull and the hydrofoil both are moving, okay, based on the 6 DOF. So this is like a combined motion for both of them. So for that we specify the dynamic mesh dict file with the 6 DOF and it is 2-dimensional motion. Okay, it's 2D motion only, not a 3D. Okay, and here inner dia, outer dia. Okay, it allows us to look at the mesh motion within the inner this inner distance. It try to look at the mesh that try exactly move like a solid body, and here in between inner to outer it try to morph the mesh. That means mesh going to change. Okay, so that is what we have: center of mass, moment of inertia, and then what we have here we are wait a minute, here, yeah, mean and u mean we specify this velocity as a internal uniform. Okay, so that is with this it's we initialize the flow. Okay, and then we say calculate with the internal field. So always it is in the one direction, it always entering with the 5 meter per second is the velocity. Okay, so that is the idea behind that, by fixing the velocity. Okay, and then on the outlet 0 gradient we have, then pressure side, okay, atmospheric total pressures, okay, and outlet we say 0 gradient. Point displacement K and omega model we are using, and for water we have a entry. Okay, so this is what we have. Okay, and on the outlet we say variable height flow rate. Okay, so depending on the movement of the wave, the height is going to change. That is the idea behind that for the alpha of water. Okay, and at the inlet it is, we are saying, is fixed with the internal field, and inlet outlet, okay, hull 0 gradient and hydrofoil, okay, K and omega entry we have. Okay, so this is how we can see the all the settings. But let's first look at the our mesh, how exactly it's look like. So we constructed in this zone very fine mesh. Why? Because this is the zone where our interface is available. So wherever the interface, we supposed to have a very fine mesh. That is the idea. Okay, and in during the near to the hydrofoil we specify very nice layers, so to capture the hydrofoil, and near the hull also we have very nice mesh we constructed, layered mesh. Okay, so that is how our mesh is look like. Okay, and then let's set up the test case. Okay, so readme file. So we are set, sorry, yeah, we are set with the mesh. So now just clean the case and copy the 0 folder. It is in 3D, so extrude the mesh to construct the 2-dimensional mesh. Okay, so 2D mesh is ready. Then clean the patch, okay, so that we don't have extra entry. Then set field, okay, to construct the wave. So let's check how the set field look like. So what we constructed water surface up to here. Okay, so and hydrofoil is completely submerged at present inside the water. Okay, and this is our entire initializations. Okay, and it is 1 cell thick. Okay, now let's renumber it. Okay, and then run the case. I'm not running the case. Okay, it for me it took almost something like, on the 4 processor I run it, and maybe 7 to 8 hours I run the case. Okay, so you also run the case. Okay, but after the simulations is over, if you see the data, okay, something like this we supposed to see. Yes, so from left side the water is entering, okay, and passing over this hull and the aerofoil, and depending on its mass and moment of inertia, it try to trigger the wave, and that wave is going to travel in the backside. So look, that is how it is happening. Okay, and here you can see the mesh motion. Okay, so it is a rigid body motions. Okay, so that is what is visible from here, and this is the zoom version, very close to what exactly happening near to this particular surface. So that is also visible from here. Okay, so this is how one can simulate the different class of the test cases for interform class of the solvers. Okay, so I suggest please go through this our different class of the tutorial and have idea about the multi-phase setting. So we didn't go on in very detailed aspect of each and every term, but our idea is to just give you the glimpse that OpenFOAM is capable enough to take into account the multi-phase class of the calculations. Okay, because this is a like a very wide area. Okay, and it is not possible to have a knowledge in each and every directions. Okay, so we just give you the idea about how one can quickly set up the test case and what is feasible inside the OpenFOAM environment as far as the Eulerian phase is concerned, or as far as the VOF is concerned. Okay, so please look at few of the test cases. Yeah, one more last thing, if you are interested in a couple of few more tutorials and everything, go to the release version tutorial area, multi-phase flow. Whatever the multi-phase flow, all the solver options is available for each and every cases. You will see all different class of tutorials. Okay, so in the runs modeling, so this is exactly DHC hull what I just showed you. That is the same test case I adapted from here. Floating object, okay, mixing sloshing tank, okay, that is also I showed you here. Then drum backing with the obstacles. Okay, so then something like a sloshing 3D tank with the 6 DOF options. Okay, so all these things is possible. So you or different motion motion is given here. You can observe that from this area. Okay, in the similar line for the two fluid Eulerian form also, we have LES based, RANS based modeling. So RANS based fluidized bed and bubble column, same way LES based bubble column, and the laminar base bubble column and fluidized bed and injection and mixing vessel class of the few things is available. You can explore it from this area. Okay, then two fluid Eulerian form, then two liquid mixing form is also available, reacting form. Okay, then multi-phase interform dynamic form available, multi-phase interform is available, multi-phase Eulerian form is available. Okay, so multi-Eulerian form here, two phase Eulerian form, two, we have a two phase, multi more than two phase but Eulerian approach. Then multi-phase interdynamic form where we have multi-phase with the interphase VOF tracking, then multi-phase form and multi-phase interform dynamic mesh motion. So both these things you can explore. Okay, so and then very another important solver is in the compressible domain, compressible interform, compressible multi-phase interform, and compressible multi-phase dynamic form is also available. So if you want to work in compressible area in the multi-phase domain, you can add up very quickly all these things, all different class of solver, and you can quickly run the test cases. Okay.